this is a discussion about exponential growth and decay models, and we start out with the law of uninhibited growth or decay. That's the slash. You're either having growth or you're having decay. And so what we see is a model function. A of t, the A is the name of the function. A of t is like f of x. So the A of t is an amount, and I've chosen A in this case to represent amount. So A of t is the amount of whatever we're talking about existing after time t or at time t. So here's the idea. For instance, suppose we have a group of, we have a culture of bacteria as an example in a petri dish. And so what this is going to do is tell us how many bacteria are present after a given amount of time. Now, time can be measured in seconds, days, hours, years, and we'll know specifically in our model how time is measured, but it will have a particular measurement. Now, the other A that we see, sometimes that's referred to as A naught, A sub 0, and really is kind of a shortcut to being saying this is how much, this is the amount of whatever we're talking about at time 0. That's the reason for that little subscript 0. But simply put, this is the original amount of whatever we're talking about. The original amount when we start measuring time. That is the amount at time equals 0. Of course, there's time before we start the stopwatch, if you will, but we're talking about how much there is when we start the stopwatch and go forward. Now, the E is the same E we've discussed before. That's the base of the natural logarithm, or is that special base. Remember, E is 2.7 something. E is a irrational number. It's a fixed number and a constant. Now, of course, I didn't mention above that T is time, is the amount of time. And we see that, of course, up there as part of the exponent. Elapsed, time elapsed. Okay? Now, we see that number K. K is a constant that is specific to the particular scenario that we're involved with. And sometimes we're given the whole model, that is, we're given the whole function. Sometimes we have to figure out what the function looks like. K is not 0, okay? It can't be 0. It could be 1. If K is a number that is bigger than 0, then we have a growth model. So that means whatever we're modeling is growing, increasing in size. In fact, in the rough idea, that model would look like this. It's growing exponentially, okay? Of course, if we made this the time axis, then we would really probably not have this portion of it. If K is less than 0, that means we have a decay model. So that means as time passes, we're getting less and less of the item, okay? And that would normally look like this, but if time is starting at 0, then we wouldn't have this part. One other thing that I'll mention here, if we take K and multiply it by 100, this is called the growth or decay rate, whatever we're referring to. Now, the reason this is called the law of uninhibited growth or decay, let me just refer to this idea again. If we have a petri dish that has a colony of bacteria in it, and we're letting it grow without any input from us, okay, for instance, if we just let it go and don't do anything to it, that's uninhibited growth. If we're experimenting and putting some kind of antibiotic to stop the growth of that bacteria, then and see if it works, well, then we're inhibiting the growth and so the model wouldn't work in that case. Uninhibited growth means that there's no outside forces acting upon it other than the natural forces. Now, let me just point out specifically here, okay, and I'll come back and we'll talk about this more, but radioactive decay, I mean, usually when we're talking about decay, we're usually talking about radioactive decay. And the model looks the same. I'm just pointing this out. It's going to be some constant, how much we start with, times e to a power that's k times t. T is still time. K is the constant that depends on the material that we're having radioactive decay on. And so when we're talking about decay model, we can depend on that K value being a negative number. And I'll tell you specifically, and I'll prove it to you a little later, that K, when we're talking about radioactive decay, will actually be 1 over the half-life of the material times the natural log of the number 1/2. Or that could be written as the natural log of the number 1/2 divided by the half-life number. Okay, but we'll come back and prove that when it's appropriate. Well, and let me also point out to you that there's nothing magical about using the function name of A, or about using the original amount called A sub 0. A just happens to be the letter that amount starts with. And so A of t is an amount at time t. A sub 0, or A naught as we call it, is the amount, the original amount of the material, or the amount at time equals 0. But there's nothing magical about using those letters. We might want to know the number of bacteria. So we might see a function written as n of t is equal to n sub 0 times e to the kt. And nothing really is new there. We're just calling things by a different name, a different letter. So don't be caught off guard by that. Well, we'll look at an example on the next page. This first example, as we read the problem, the number of bacteria represented by n, or n of t in this case, present in a culture at time t, and t is measured in hours, obeys the law of uninhibited growth. And we're given what the model is specifically here. So later on, we're going to run into scenarios where we have to decide what the model is. And when we're deciding what the model is, and what we're really worried about is determining this value, which is the n sub 0 or the a sub 0, and this value, which is the k. Now, because this is a set of, this is law of uninhibited growth, that k is positive. Remember, that's when we're growing. So and so in this case, we might identify the n sub 0 rather than saying a sub 0 as 1,000, okay? And the k value, just to make a point, is a 0.01, okay? Now, here's the first part of the problem. There's several parts. Determine the number of bacteria at time equals 0 hours. Determine the number of bacteria at t equals 0 hours. Now, we ought to be able to do that directly because remember, n sub 0, that number 1,000, represents the original amount. And the original amount is what amount there is when we start measuring time at time 0. But it's nice to know that the formula itself will give us this. Because what we would do is say, okay, time is 0, so we want to know the number of bacteria we have, so we put our t value of 0 into the function. And so we would calculate, well, that's 1,000 times e to the power 0.01, and our t is 0. But now, 0.01 times 0 is just 0, so this is 1,000 times e to the power of 0. And of course, e to the power of 0 is just a 1, and so we have 1,000 times 1, or 1,000. That's the reason it works the way it does. You know, in this model, anytime t is 0, we have e to the 0 or 1, and so it's that factor in front of e to the power that is the original amount. Okay, that's just another way to see that. In part B, what is the growth rate of the bacteria? Now, if you remember on, bacteria. If you remember on the previous page, we said growth or decay, but this is a growth model. Growth rate is the k times 100. And see, that's going to give us a percent. Multiplying by 100 is giving us the percent. Well, in this case, k is 0.01. And when we multiply that by 100, that gives us 1. 0.01 times 100 is 1. So the growth rate is a growth rate of 1%. Okay, part C. What is the population for the number of bacteria? What is the population of the colony, or the number of bacteria, after 4 hours? Well, really, here's all we're asking. T is equal to 4. T is equal to 4. So we want to know n of 4. That means we replace t with 4. So we'll have 1,000 times e to the power that is 0.01, and our t value is 4. Now this is going to require some calculation. It's going to require a calculator, but let's do a little work ahead of time. 1,000 times e to a power, when we multiply 0.01 times 4, we get 0.04. And so now we would get our calculator out and just simply type in the pieces that we need. Okay, that's the exact amount, but if we type in the pieces that we need into our calculator, then we should get approximately, and I've rounded it, 1,040.81. Now, let's be real about this. Depends on how we're asked to answer the question. Now, here we're talking about bacteria, and you can't have 0.81 of a bacteria. So if I was answering this in the real world, I'd say, well, since we can't have 0.81, and we don't have a whole one, we would say this is 1,040 bacteria. But in my math lab, or whatever your homework is, it may ask you to round it to 1/100ths or something like that, 1/100ths. Okay. Okay, let's look at the next problem. We'll continue this. Let's see, when, or the next part, when will the number of bacteria reach 1,700? So we're looking for a t-value, aren't we? And what t-value are we looking for? We're looking for a t-value that when we put it into the function, the number we get is 1,700. In other words, we're looking for the left side of the equation. See, that's really all that we've got here. N of t from the model is 1,000 times e to the power 0.01t. And if we know that we want the amount to be 1,700, that means the left side of the equation is going to have to be 1,700. And what we're trying to do is we're trying to solve for t. And if you look at what we've got here, we've got nothing more than an exponential equation with the unknown t in it. And so to solve that exponential equation, we need to isolate the exponential part. So we need to get that alone. So we're going to divide on both sides by 1,000. So we'll end up with, and by the way, I'm going to put my e to the power on the left side. And when I take 1,700 and divide by 1,000, then it will look like that. Now, I don't want to write this as a decimal because don't want to approximate too early. But certainly 1,700 over 1,000, I could write a little nicer, although it's not required. That is 17 over 10, isn't it? Which we could say is 1.7 exactly. But now to solve this exponential equation, what would we do? We'd take the natural log of both sides, wouldn't we? That's a 1 there, equal to natural log of 17 divided by 10. I'm kind of cramming these things in there. And then I have 0.01 times t, bringing the exponent down, times the natural log of e is equal to the natural log of 17 over 10. Now the nice thing about it is the natural log of e is just 1. So this equation ends up looking like 0.01t is equal to the natural log of 17 divided by 10. And so if I want to know the value of t, I'll just simply divide both sides by that 0.01. So I'll have a numerator that's the natural log of 17 divided by 10 divided by the number 0.01. And now I would get my calculator out, and I would go from there. So when I use my calculator, I get rounded to tenths, 1 decimal place, 53.1. Now be careful, what is this? Time is measured in hours, isn't it? So this is about 53.1 hours for the bacteria to grow from 1,000 to 1,700. That's more than a couple of days, isn't it? Okay, so let's do one other part to this problem, and we'll do that on the next page. Okay, although I kind of bundled up the sentence, the part E is to answer the question, when will the number of bacteria double? Now, I might tell you that this is not really a well-defined question, because double from where? You know, I mean, I guess right now we're thinking the original amount. See, we're thinking that we're starting with 1,000. But in the last problem, the question was, well, how long will it take to reach 1,700? So now maybe we're being asked, how long does it take to double from 1,700, the amount of bacteria we have? Well, let's do it with 1,000, and then we'll see where that leads us, okay? So let's assume we're wanting to double the original amount. So we're doubling the original amount, and the original amount was 1,000. So that means we're looking for a t value that will make n of t double of our original amount, 1,000. So that means we need the amount of bacteria to be 2,000. So on the left side, we have our 2,000. That's how much bacteria we want to have, and we got to figure out the time it requires to get that. Now the other side of the equation or the model looks like this. So it's the t that we're looking for that causes the left side to be 2,000, double the 1,000. Now, this is just another exponential equation, isn't it? So we need to once again isolate this part of the equation. So we'll divide on both sides by 1,000. Okay. And of course, 2,000 divided by 1,000 is just 2, isn't it? So this is e to the power 0.01 times a t is equal to 2. And so, as we did before, what we would do is take the natural log of both sides. Okay? And that will allow us to bring that exponent down as a factor, and we'll have times natural log of e alone is equal to the natural log of 2, of course. Well, the natural log of e is 1 once again, so we have 0.01 times t is equal to the natural log of 2, and to solve for t then, we divide on both sides by the decimal 0.01. Now, if we approximate that with our calculator, and we need to, because it really doesn't tell us a whole lot, we would get 69 point, and I'm rounding to 1 decimal position, tenths, 69.3, and of course we're measuring time in hours. So to double the amount of bacteria, if we start at 1,000, is going to take 69.3 hours. Now, let me remember I said that this was maybe not really well defined. We weren't quite sure what we were starting with. So let's assume, okay, that, let's not go with a specific amount. Let's assume we start with n sub 0. See, that's the original amount of bacteria. Start with n sub 0. How long to double? Okay. So we're wanting to know the t value. Okay, we're wanting to know a t value so that the left side, the amount we have, is equal to double the amount that we start with. Double the amount, and what did we start with? N sub 0. Well, what's double that amount? 2 times n sub 0. That's double that amount, isn't it? So what that's telling us, if we're starting with an amount called n sub 0, then the amount we want after our time, we don't know what time it takes to make the amount we have double that amount. But remember, what we're starting with is n sub 0. So instead of having a 1,000 in this position, we would have an n sub 0. And it would be times e to the power 0.01 t. Now, it looks like we don't have enough numbers to solve this for t, but if we were to solve it for t, we would need to isolate this portion, so we'll divide out this n sub 0. So on both sides, we divide by n sub 0. Now, when we do, of course, this is going to, the n sub 0 is going to divide out, and we're going to get 2. Of course, the number on top is twice as much as the number on bottom, and so when we do that division, we will get 2. And this looks exactly like what we had above when we knew the starting amount was 1,000 bacteria. So as we solve this, we'll get exactly the same solution. See, we're solving exactly the same equation, aren't we? And so I'm not going to go through the solution of that. You can look above, but we'll get t is approximately equal to 69.3 hours. So what this is really telling us, in this model, for this culture of bacteria, it doesn't matter how many bacteria we have, to double the amount that we have is going to take 69.3 hours. So even if the bacteria grow to 2,000, to double that to 4,000 will take 69.3 hours. Okay, well that finishes this first problem. We're going to look at some other problems where the model is not given to us. We have to decide what the model is, the function or the equation, whatever you want to call it. We have to decide what the model is. And of course that takes a little different effort. You can see in this next problem, as it's stated, a colony of bacteria increases according to the law of uninhibited growth. Oops, I made a mistake, as you can see. If the number of cells doubles in 5 hours, find how long it will take the colony to increase from 10,000 cells to 25,000 cells. So the first thing we notice here is we're not told specifically the model. We know the form of the model, and the form of the model is one of uninhibited growth, law of uninhibited growth. And so generally that says that the model looks like this. The number of bacteria or the number of cells is equal to the original amount n sub 0 times e to a power, and the power on e is k times our variable t for time. And so we don't really know all that we need to know, and that's really the issue here is we don't know. I guess we do know n sub 0 is 10,000, don't we? Okay, so we know that. And since we know that n sub 0 is 10, and actually we didn't even need to know that n sub 0 is 10,000, all we need to know is it doubles in 5 hours. The number that we have doubles in 5 hours. So I guess what we could say is that if t is equal to 5, then that tells us that 2 times the amount that we start with is equal to the amount we start with times e to the power k times, now our t, remember, is 5. The issue is, no matter, it says that the number of cells doubles in 5 hours. So if we start with n sub 0, when t is 5, we'll have 2 times n sub 0. And so, of course, what that tells us, what we get from there, we divide both sides by n sub 0, and we get 2 is equal to e to the power 5k. And so we solve that exponential equation by taking the logarithm of both sides. So we have the logarithm of 2 is equal to the logarithm of 5k, which is just 5k. Remember, it would be 5k times the log of e, but log of e, natural log of e is 1. So what we end up with here is that k itself is the natural log of 2 divided by 5. That's the exact value. Now, I probably prefer to approximate that. Okay, I prefer to approximate it, but we need several levels, levels, if you will, of accuracy. So I'll round it to 4 significant digits. So I'll get my calculator out to do that. So I get 0.1386, and 4 significant digits here would be 0.1386. I wouldn't round it any less than that. So here's now what we know for sure about our model, okay? Regardless of the amount we're starting with, but in this case, we do know that we're starting with 10,000 cells. So n of t is going to be equal to 10,000, okay, that's n sub 0. We're starting with 10,000, times e to a power k times t. And we just found out that k was 1386 times t. So there's our model. And we haven't answered the question yet. We just had to get the formula or the model for this particular set of bacteria. So what we're wanting to know then is what t causes n of t to be equal to 25,000, because we want to go from the 10,000 we're starting with to the 25,000 goal. So we'll end up with, on the left side of our equation, 25,000, this becomes routine now, doesn't it, is equal to 10,000 times e to the power 0.1386 t. And so we'll divide on both sides by 10,000. And when we do, well, this is what it will look like. E to the power 0.1386 t. Now 25,000 over 10,000, I don't really need to simplify that, but I can without a great deal of difficulty, so I think I will. Certainly 25 over 10, and 25 over 10 would be 5 over 2. So that whole 25,000 over 10,000 simplifies to 5 over 2. So we take the log of both sides again, natural log, and when we take the natural log of the left side, you'll note that we get 0.1386t. We've been through that multiple times, haven't we? See, because the natural log of e to the power 0.1386t, we would bring the exponent down. There's the exponent, and then we say times natural log of e. But the natural log of e is 1, so it leaves only 0.1386t. Is equal to, remember, we took the logarithm of both sides, natural logarithm. So the right side has natural logarithm of 5/2. So when we divide on both sides by the coefficient to solve for t, we'll have t is equal to natural log of 5 over 2 divided by 0.1386. And when I use my calculator, let's see, I should get, as I said, t is approximately, as I do my calculations with our calculator, 6.61 hours. I know the time is kept in hours. So there we have it. And the big deal here is that we weren't given the model, but we were given enough information to calculate the model. And the most important part about calculating the model, of course, was finding the value k. And that's what we had to do before we finished the rest of the problem, or actually did the problem. Okay, well, let's look at another problem that's very interesting here. And I'll do that on the next page. This is a very interesting problem that we're looking at here. I guess in an archaeological dig, bones are found, or at least a bone is found, and it's found to have 45% of the original amount of carbon-14. If the half-life of carbon-14 is 5,600 years, how old is the bone? Before we do this problem, let me point 2 or 3 things out. First off, radioactive decay or decay, and not everything that goes through radioactive decay is dangerous to us. There are certain kinds of radioactive decay that are dangerous. Now, what does it mean to be radioactive or to have radioactive decay? Well, some people think that, okay, we've got this radioactive material, and as it decays, the material disappears. Well, really what that means, really what's going on, is that if we have a material that is quote, radioactive, it means that that material is an unstable isotope, which means that it will, for instance, lose electrons, atoms lose electrons, and when that happens, the atom changes. It goes from one type of isotope to another, one that is stable. And so it's not that the material just disappears, we call it transmuting. That you may have, if you will, the same amount of material, but part of it is the original material and part of it is a new material caused by the decay. So that's the first thing I want you to know is when we have decay, it doesn't mean the material just disappears. It means it changes form into another type of material. Okay, it's called transmuting. Now, the second thing, this is about carbon-14. A bone is found that have 45% of the original amount of carbon-14. All living material, all living things on the planet Earth, whether they be human beings, whether they be trees, whether they be plants, whether they be bugs, they all have carbon-14 in them. And we know how much carbon-14 is in living material. Okay, we know how much carbon-14 is in our bodies, in the cells of our bodies. So carbon-14 is unstable. So when a living organism dies, then that carbon-14 begins to decay. Now, obviously, it decays very slowly because it says the half-life is 5,600 years. So it decays slowly, but when we look at something that has been dead, like a bone, we measure the amount of carbon-14 that is in it compared to what it should have been when it died, then we can use that information to date the age of the material, the bone in this case, and that's called carbon dating. That's what it's called. Now, another thing, what does half-life mean? Half-life is the number of years it takes the material to decay by half. So whatever it is, if we have a pound of material and you have a 5,600 year half-life, that means after 5,600 years, it will have decayed, so now there's only 1/2 of the original amount. In this case, 1/2 pound is what we're talking about there. So that's the idea of half-life. Okay, well, let's start on this problem. And the main thing about this problem is that we're going to assume that this is modeled by the law of uninhibited decay. And so we would have I'm going to call it amount because we're not really talking about numbers here. We're talking about the amount in weight, most likely, or mass. So the model will be of this form. A of t is equal to a sub 0, the original amount of material, times e to the power kt. Now, once again, we really don't know. There are two things we don't know. We don't know the a sub 0. We don't know the original amount of material. And we don't know k. Those are the two things we don't really know, I suppose. Okay? So, here's what we're going to do. The first thing we're going to do is calculate k. Okay? We need to find k. And the way we're going to do that is we're going to use the half-life information. That's what we're going to use. So let's assume the original amount is equal to a sub 0. That's a reasonable assumption. So when t is equal to 5,600 years, then a of t, the amount we have after 5,600 years, will be 1/2 of the original amount. That's why it's called the half-life. Well, of course, we could write that as, well, let's just write it that way. That's fine. So here's what we've got then. When t is equal to 5,600, what would our model look like? Well, we would have 1/2 the original amount if the original amount was a sub 0, times e to the power k times t, which is 5,600. Now, obviously we don't know a sub 0, but we're trying to find k. And if we divide both sides by the original amount, then we would end up with 1/2 times a sub 0 divided by a sub 0 times is equal to e to the power 5,600 k. K times 5,600. And of course, on this left side, we're left with just 1/2, aren't we? When we cancel or reduce. So we have e to the power 5,600 k is equal to 1/2. I want some space below, so I'm going to come over here to finish this out. So we would take the natural log of both sides because we're solving for k. Okay, natural log of both sides, and then we would say, I mean, we could bring the exponent down, or we could say, what power do we put on this base e that gives us e to the 5600k, and it would just be 5600k, wouldn't it? We could go through the same steps that we've gone through before. And then to solve for k, of course, we would divide both sides by 5600. And then we would approximate the value of k. And we want several significant digits. So let me do this calculation. Okay, we would get in rounded form, but I'm rounding to 4 significant digits, 0.0008183. Now, it's different saying rounding to 4 decimal places as to rounding to 4 significant digits. The 000 are not digits that are significant. It's the 8183 that are significant. So that's the reason I set it the way I did. If we rounded to 0.0008, that wouldn't be a good enough approximation for k. So now we have the value of k, which means we have, our model. Now, almost, I guess. Okay, so let's pause here now. In general, now our model looks like, I say pause, I mean I'm coming down here. Our model looks like, well, the a of t is equal to the original amount, a sub 0 times e to a power now, k times t, and since we know k is 0.0008183, then this is what our model looks like. Now, the problem, of course, is we don't know the original amount, but in this problem, it doesn't matter. We just assume a sub 0 is the original amount. Now, read the problem again. Okay, we don't know that original amount, but what it says is today, the amount we have now is 45% of the original amount. Okay? And so we want to know the time that it took to go from a sub 0 amount to 45% of that. So now, see, for t, we want to know for t is equal to what, that n of t, excuse me, a of t is what we're calling it, my bad, a of t is equal to 0.45 times a sub 0, 45% of the original amount. And so that gives us the equation, 0.45 a sub 0 is equal to a sub 0 times e to the power 0.0008183t. And you see we have an equation to solve. Well, I'm trying to solve for t. Remember, that's what we're trying to do, solve for t. So I need to isolate this exponential portion, so I divide both sides by this a sub 0. And when I divide both sides by a sub 0, on the left side I end up with just 0.45, and on the right side I have e to this really ugly exponent. I'll take the logarithm of both sides, so it's the natural log, that is. So I take the natural log of 0.45, and it'll be equal to the natural log of this right side, and we've been through this several times, and that will just give us the exponent, won't it? And so when I'm solving for t, I need to divide out this decimal. So t is equal to the natural log of 0.45 divided by 0.0008183. And that's approximately, now remember, that's the time it would have taken, so the age of the bone, the time it would have taken for the original amount of carbon-14 to decay so that there's only 45% of it left today, because that's what we're measuring, how much we have today. And when I do this in my calculator, let me do that. Oops. So if you've been following along, and I hope you have, and maybe checking me once in a while, I made a mistake way back up here in my calculator. There was an extra number that got put in there. And the value here is actually, my bad, it's negative. And of course, that's what we would expect it to be, is negative, because this is a decay model. I should have caught this earlier. Negative 0.0001, and remember I'm doing this to significant digits, 238. So that means what I've got here is incorrect. It means this is incorrect. It means this is incorrect. It means this is incorrect, and this is incorrect. My bad. Okay, so let me come over here and correct that. It's just the numbers that I've got incorrectly here. So this should be 0.45 a sub 0 is equal to a sub 0 times e to the power negative 0.0001238 t. And so here, when we divide on both sides by a sub 0, we get 0.45 is equal to e to this power, negative 0.0001238 t. And then when I take the natural logarithm of both sides, and on the right side, I'm going to get this exponent, negative 0.0001238 t. And then I'm going to divide by that decimal, that negative decimal, and so I'll have t is equal to the natural log of 0.45 divided by the negative of 0.0001238. Now, when I use my calculator to approximate that, and I'll do that now, I think I'll have it correct. I know I'll have it correct. 6,450 years. That bone that we have found, based on the information we can get from it, is over 6,400 years old. Okay, let me remember when I talked about radioactive decay at the very beginning, radioactive decay, and I said in the case of radioactive decay, then the K value, radioactive decay, the K value in the model, the K value is the natural log of 1/2 divided by the half-life number. Remember me saying that at the very beginning? And look down here. Look right here. The K value we calculated is the natural log of 1/2 divided by 5,600, where 5,600 is the half-life years, or the half-life time. It's not always counted in years, but here it was. And so you can imagine, how did we do that? See, how did we do that? Well, the 1/2 came from this step right here. Okay, it came from this step. We said, okay, if I use the half-life amount, which is this 5,600, if I use the half-life amount, then as my time, then the amount I have after that time is 1/2 the original amount. So there's the 1/2, and then there's the half-life amount. And if we just follow those through, the a sub 0's on the next step leave only 1/2 on the left side of the equation, right? And we still have the the half-life time as an exponent, a part of the exponent, half-life time times k. And so when we took the logarithm of both sides, we ended up with the half-life amount, and it doesn't really matter that it's 5600 here, it's just the half-life amount. It would have worked the same way, whatever that was. And of course, the 1/2 came from that original equation that we were working on. And so that's where that natural log of 1/2 comes from, and that's where the 5600 or the half-life time comes from. So we more or less have proven this idea, and we could in the future just use that idea if we can remember it, rather than go through this first set of calculations that we did. Very interesting. Well, I want to do one other type of problem here, and it's about Newton's law of cooling. Well, let's first talk about Newton's law of cooling. Now, it takes calculus to come up with this equation, but this is what Newton's law of cooling says generally, that the rate of change in the temperature of an object is proportional to the difference between the object's temperature and the temperature of the surrounding medium. Now, basically, it means there's some kind of prediction that if you take, for instance, a coffee cup full of hot coffee, then that coffee is going to change temperature in some way based on the room temperature that the coffee is in. It's going to cool off, and it's going to cool off at a certain rate. And we can calculate the anticipated temperature of the coffee at any given time. Or if we take a piece of hot metal that we've heated up and we throw it in water, well, now the surrounding medium in this case is the temperature of the water. And so that hot object put into this water is going to cool down, and it's going to cool down at a certain rate. This is also done in determining basically the length of time since death. For instance, in a murder case or something like that, they can measure the internal temperature of the body, and they can also compare that to the medium that the body is in, the air temperature of the room that the body is in, and they can predict then how long that the time since death, because that body will cool a certain rate. So what I've written up here is T sub object is equal to T sub surrounding plus C times e to the kt power. Now the lowercase t represents time, so that's time right here. And time may be measured in minutes, hours, days, however it's going to be measured. Now the T sub object, this is the temperature of the object at time t, okay? And so we're assuming t starts at 0 when we're measuring the change in temperature, starts at 0. Okay. Now the T sub surrounding okay, this T. This is the temperature of the surrounding medium, okay? Temperature of the surrounding medium. Whether it's the temperature of the water something's thrown in, or the room temperature, or we take it outside and put it in snow, the temperature of the snow, whatever, the temperature of the surrounding that the object finds its place in. And you can see this value C is a constant, and what it is the difference between the original temperature of the object, like when we take it out of the oven, or when we pour the cup of coffee, what the temperature is then, minus the temperature of the surroundings. So it's the difference between the original temperature and the temperature of the surroundings. So let's look at a problem based on this. Now, not all books write it the way I have, but I hope that this is what you can easily remember. Okay? I hope you can remember this. And that's what we're going to use, at least in this problem. So let me write the problem down. Okay, here we have an object that's heated to 90 degrees Celsius, and then after it's heated, it's allowed to cool in a room whose air temperature is 25 degrees Celsius. If the temperature of the object is 75 degrees Celsius after 10 minutes, when will its temperature be 50 degrees Celsius? That's a little bit hard to read. As I'm looking above at my equation, the Newton's law of cooling, I probably would have been better off to help you if I wouldn't have written temperature of object there, that just allow T to be the temperature of the object after a time of T, lowercase t. So T is going to be equal to the temperature of the surrounding medium. Well, here the surrounding medium is the air in the room that the object is cooling at, okay? So that temperature is 25 degrees. That's the T sub surrounding. Plus, now here's what we've got, it's this value C. Well, the way we calculate C is we take the original temperature of the object, which is 90 degrees Celsius, and we subtract the surrounding medium temperature, which is 25 degrees Celsius. So that's the value C. And of course, we can do that calculation here in a moment, times e to the power k times t. Now, we've seen this before. As we simplify this, we have t is equal to 25 plus, now 90 minus 25 is 65. So our model looks like this, but we don't know the value k yet. It depends on the object and how quickly a particular object will cool down. So we've got to calculate k. Well, we have to use the other information that we've got, because the other information that we have that says if after 10 minutes, if the time is 10 minutes, lowercase t is 10 minutes, then the temperature of the object, which is indicated by a capital T, is equal to 75. And that information we can put into this equation, and then the only unknown would be k. So we put a 75 over here on the left side is equal to 25 plus 65 times e to the power k times t. And t is 10. So we'll say 10 times k instead of k times 10. Now all we need to do is solve that equation for k. So first we'll subtract 25 on both sides. 75 minus 25 is 0. There we go. Then we divide out the 65. So I have 50 divided by 65 is equal to e to the power 10k. And we can simplify the left side. We don't really need to. We could just take the natural log of it, because we're taking the natural log of both sides, of course. And on the right side, when we take the natural log, we're left with just the exponent. We've been through this multiple times. And so if I'm solving for the value k, then k will be equal to the natural log of 50 divided by 65, and all that is divided by 10. And that's approximately equal, and I need to get plenty of significant digits here. So that calculation of K, now this time I decided to get 5 significant digits, which is probably better than what I did earlier. So I get K as a negative value because we're expecting that this is a decay of temperature, isn't it? So we would expect K to be negative. So it's negative 0.026236. Now, having done that, now we have the full model for our problem. We have T is equal to 25 plus 65 times e to a power that is negative 0.026236 times our time value, T. That's a 236. Hard to read. Now the question is, when will its temperature be 50 degrees centigrade? When will T, that T, be equal to 50? And so we'll put that T, that temperature 50 in, and we'll solve for the time, which is lowercase t. So we'll have 50 is equal to 25 plus 65 times e to this ugly exponent, which is negative 0.026236t. Subtract 25 on both sides, so I have 25 is equal to 65 times e to that power. Whoops, 26236. I'm sorry for that being so messy. Then divide by 65, so we'll have 25 divided by 65 is equal to e to this power, negative 0.026236 times t. Now we'll take the natural log of both sides. The natural log of 25 over 65 is equal to the natural log of the right side, which will only be the exponent, which is negative 0.026236t. And so when I'm calculating t, I'm dividing out that ugly decimal. So I'll have natural log of 25 over 65, and that natural log is divided by negative 0.026236. Okay? And so when I approximate that with my calculator, let's see what we get. We get approximately 36.4. Now our measurement in time, remember we did this whole thing based on 10 minutes. So 36.4 minutes is how long it will take this to cool from 90 degrees to 50 degrees in a room of 25 degrees. Pretty cool, huh? Well, that's all I'm going to do with these types of problems. I think that this should be enough variety so that you can get through all of your homework. Good luck to you.